Hello everyone, I am Partha. Today I'll discuss the topic for which the Nobel Prize in Physics for the year 2022 was announced. This year's Nobel Prize in Physics is shared by three physicists, Alain, John F. Clauser and Anton Zeilinger, for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. I'll try to explain it simply so that everyone can understand it. Prior to the 20th century, everything about the physical world was understood easily by the laws given by the great Isaac Newton. These laws of so-called classical physics works well in our daily life. If we know the initial conditions, we can precisely predict where a cricket ball will be at any instant. We can calculate the position of a rocket at any given time. We can calculate the orbit of the moon around the earth precisely. This world governed by classical physics is deterministic. But in the early 20th century, when the scientists began to explore the micro world, that is the world of molecules, atoms, electrons, photons, etc., it was found that the laws of classical physics cannot predict the behavior of these subatomic particles. So, in order to study the subatomic world, a new way of understanding known as quantum mechanics was developed by Max Planck, Albert Einstein, Niels Bohr, and many other brilliant minds. While in classical physics everything is predictable with accuracy, quantum mechanics is highly probabilistic. For example, in classical physics, we can precisely predict the whole trajectory of a ball if we know the initial conditions. But in quantum mechanics, we can only find the probability of a particle to be in a particular state. Einstein didn't like this probabilistic nature of quantum mechanics at all. He famously said, God doesn't play dice. Let me try to give an analogy of particles' behavior in quantum mechanics. This is a coin. One side is head, the other side is tail. We all know that. If I spin the coin like this, we cannot say whether we see a head or a tail now. We can see whether it is a head or a tail only when we stop it. Now this is known as a measurement in quantum mechanics. This measurement can be a test or an experiment. Before a measurement, quantum particles are considered to be in a mixed state or a state of superposition of all possible states, say head and tail for this particle, and it can show any one of the states upon measurement, either head or tail. The result is highly uncertain. Einstein didn't like this non-deterministic nature of quantum mechanics. Einstein, with his two colleagues Podolsky and Rosen, wrote a paper in 1935 describing the nature of a type of particles known as entangled particles. Let me first discuss about entangled particles. Let us consider a pair of particles produced from a particular quantum system in such a way that if we do a measurement on one particle and find it in a particular state, say head in our example, the other particle will be found as tail. Now we have to remember that according to quantum mechanics, these particles were in a mixed state of both head and tail before the measurement. Before a measurement, both the particles show equal probabilities of being head or tail. But when we perform a measurement on one particle and let's say it comes out to be head, the probability of the other particle to show a tail becomes 100%. As if the particles were communicating among themselves instantaneously. This phenomenon is known as entanglement. If these entangled particles are separated by a very large distance, still they stay entangled. But as we know that no information can move faster than the speed of light, so this instantaneous communication allowed by quantum mechanics between these entangled particles was something that Einstein could not digest, and he called it as spooky exchange at a distance. In the EPR paper, they reported that our understanding of the quantum world is incomplete. They also wrote there must be some hidden mechanisms with which the particles decide what they are going to show up when measured. This is now known as hidden variable theory. In simple terms, the theory means that the particles don't stay in a mixed state or in a state of superposition. They are distinctly different at the formation itself. That means a particle that we found out to be head after measurement was head even before the measurement. This theory was impossible to test until 1964. Now let me explain why it is difficult to test. Here comes the difference between my analogy of the coin and the real quantum world. In the case of this coin, we can see the mixed state before we stop it. But this is not possible for a subatomic particle. We can see it only after a measurement is made. And after the measurement, we can find out in which state it is now. But we cannot know which state it was in before the measurement. It took 30 years after the EPR paper to actually develop an experimental technique to test this hidden variable theory. John Stuart Bell in 1964 wrote a paper where he showed mathematically how to test this theory. That is a mind-blowing technique and very difficult to explain in simple terms. He basically proposed an inequality that arises when two observers make separate measurements on two entangled particles considering local hidden variables exist. The first test of Bell's inequality was performed by an American physicist, John F. Clauser, in 1972. Then in 1982, the second test was done by Alain. Both the experiments showed violations of Bell's inequality theorem, but there remained a few loopholes. Finally, in 2017, a loophole-free test was performed by Austrian physicist Anton Zeilinger, which confirmed the violation of Bell's inequality, and hence EPR's hidden variable theory was rejected by the scientific community. The development of experimental tools to investigate and control entangled particles has laid the foundation of a new era of quantum technology, such as quantum computation, quantum teleportation, cybersecurity, and quantum cryptography.